Okay, let's get started. Questions? No. Well, you asked everything. All right, let's get started. Let's finish up a classical aspect of Iraq, Lagrangian today, and then we start quantization. Okay? So last time we look at the Dirac equation, right? And then we solved it. We found the solutions by saying, well, we look at the equations, and then we solve the equation by first going into the zero momentum limit. And then we found out that if you go to the zero momentum limit, Dirac representation is slightly more useful than Weyl representation, because if you recall, in this limit, one of the equations that we had to satisfy is this, and then similarly, is zero. It had to satisfy that. So, but then we noticed that in Weyl representation, beta mixes up components. But then in Dirac representation, it cleanly separate up and downs, right? So that's why we decided to go to that. And then it was very quick to find solution. Like this is literally finding two orthogonal bases, either upper two component or lower two component. And then we boost it to generate a solution for arbitrary momentum, right? So that's how we will look at it, right? By the way, this was for by looking at that was for positive frequency solution, and then this was negative frequency solution. So if you like, you can think about this part to be particle and this part to be antiparticle, as we will talk more about it. So yeah, we solved it, and then we look at the solutions, and then we discuss some properties of a solutions as we talked about. Now, one of the things that we talked about last time was there's a normalization issue. And then the way we normalized, for instance, was in such a way that this is just reminding what we talked about last time. For instance, we normalized so that, and then there was indices, right? Because there were two components, the R, S. We normalize of that, we satisfy this relation. And the same thing for B. Okay? So that's what we talked about. And then I think I mentioned what Coleman called the Pauli's theorem. So now I'm going to quickly go through this argument and then move on. So what was the statement? Looks like we started out by saying, oh, Dirac equation can be conveniently written as this way, where we found out that these alphas and betas satisfy somewhat accidentally, these sort of relations. Well, beta. Okay. So until last time, it was like, nice observation. Okay. If we observe that, we can package things together in this form, and that looks like everything good. And then the Pauli's theorem statement was providing somewhat deeper insight or justification of all these constructions. So what was the statement? Basically, for any, since I wrote down long, more precise statement last time, I'm just gonna state a slightly way. So for any set of now alpha and for the beta, again, now this is a set. This is an anticommutator that I'm looking at. And recall, all of these are 4x4 matrices. So I'm talking about set of four 4x4 matrices. And then all this thing we call Dirac algebra or Clifford algebra. And then, since I'm talking about 4x4, I'm explicitly talking about four-dimensional quantum field theory and fermions in four-dimensional quantum field theory. So for any set of that is equivalent, any form of set that satisfies Dirac algebra is equivalent to Weyl representation, if you like. I mean, not that Weyl representation is so special, but the reason why here we're picking up particular this Weyl representation was that's how we decide to write Dirac equation that way, right? Started out with the Weyl, each of the u plus u minus, we combine it this way as a now bookkeeping machinery back then, and that was done in this particular format, right? And then we talked about change of basis with the Dirac. And then there was a more mathematical content of that, and the physical content of that was the following. So if somebody had me, so here the statement is the given again alpha beta, again, that satisfies Dirac algebra, then this provides representation of spin half, or if you like spin half representation, if you like this. So if somebody handed me this set of this algebra, sorry, this matrices that is on this algebra, simplify a spin half representation of Lorentz group. Okay, so that's the first statement. Therefore, this is enough input, again, with this construction, this algebraic structure. Therefore, this will lead to theory of Dirac fermion, almost immediately, by which I mean, in particular, I'm talking about theory of this representation. Okay, so that's the thing that I mentioned last time, and let's quickly see how that is true. So we will spend this time, most of the time on this side, and then I'm just going to make a quick comment on this side. So let's start out from there. So let's start out with let's assume there are alpha and beta such that Dirac algebra holds. Okay. Then let's define as a boost generator. Let's define this. Okay, you might say, oh, did I know this is the good generator? Okay, you might say that. One way to see that was, remember, we already knew how boost generator looked like. Because recall, this is literally recalling what I'm talking about. So you recall this. Yes? So if you had a four-component Dirac fermion in the Weyl representation, you knew what is the shape of the boost generator in that form, right? So in other words, now if I take this guy that acts on the u plus and u minus, which was the Weyl, this immediately tells me that this has to look like how. This is half sigma, this is also half sigma, acts on the upper two component, acts on the lower two component, and that looks like what? Exactly that. So there's I, let me pull that out, and then minus sigma, and then there's over 2. And then if you recall, that was exactly alpha defined in the Weyl representation. Okay, so we knew that. So let's start out with this, and then we're going to generate the Lorentz rotation, demanding that it has to satisfy Lorentz algebra. So is the logic clear? So what am I saying? I am starting with this one that satisfies fulfills the Gerard algebra. And then I'm just gonna take this as a initial definition of the boost, and then I'm gonna generate the rest of the generators, and then check that they all satisfy required the Lorentz algebra. Okay, so that's this first one. So if you work this out, you will find that this K is given by, okay, let me see, okay, this. Okay, this is just explicit algebra you can plug in and check. Is so far clear? I just literally plug this in and it worked out. Okay, using one of the epsilon Lebesgue symbol identity. You know. Okay, so let me repeat it. AJK, AJL. This is Euclidean, so it doesn't matter whether it's upper or lower indices, okay? This is 2 delta. Okay, you can just literally check it. Another useful way of actually writing Lorentz algebra is as follows. So let me give you another expression. So let's literally plug in. So what do I get? So the left hand side, so on the right hand side, I get this. IJK, LK. What do I get on the left hand side? So if I plug back in, I get 1/4. This, right? So so then what I can do is I can multiply this expression with I epsilon, say IJF. Okay, so if you do that, what do you get? So L sub L, okay, that was not best choice. Nevertheless, I picked it, too late. Is equal to, what do you get? 1/4, 8, plus, minus 1/8, and then there must be epsilon, I, J, L, alpha I, alpha J. Okay, so I just literally did it, but there's a double counting. If I pick 1, 2, 1, 2, and then if I pick 2, 1, 2, 1, antisymmetrize, they give the same answer. Are you with me? Right? I pick 1, 2, 1, 2. It's the same as 2, 1, 2, 1 because they both are antisymmetric. They add up. So this has a double counting. I'm just saying that for now, but later this expression will be useful. Okay. So for instance, from that definition, you can get, I don't know, L over X is equal to, it's literally like I/4. So if I have X like, right, so that's the non-trivial component, so it gives me YZ. So and so on and so forth. You can now just write down everything you need. Good. So to finish up this part of the discussion, what do I have to do? So well, I defined boost generator, and then I generated a Lorentz rotation generator out of this Lorentz algebra, and then we know one more thing to check, which is if I had a rotation acting on a boost, it shows that boost generator behaves like a vector. This equation is exactly capturing that. Try to do one of the Lorentz algebra. So, I mean, if you like, you can do it in a most maximal general way by keeping general expressions which I gave you. So MI looks like that. Now I will give you LK looks like you can plug in and then use a Gerard algebra to check that holds. Okay, so that's good exercise to do. But if you don't like, then you can also do explicitly. For instance, okay, let me just look at explicitly this because I'm too scared to hold all these epsilon tensors. So if you don't like that, just plug in and do it. Minus 4, I don't know, times I/2, alpha y, alpha z, alpha what? What? Okay, so that's what? Y, z, y, minus y, z. But now I'm going to only use Dirac algebra. Dirac algebra told me that this is anti-commutative, it should be that. Then Dirac algebra told me that that should be 1. Okay, so that gives you minus 2 times alpha that. If you plug back in, you should see this is true. Okay, so you can do it. What else? Yeah, I think I do. Okay, so therefore, what I have just demonstrated is that just from this set of 4x4 matrices, I can generate entire set of a Lorentz boost and rotation in such a way that it certainly satisfies Lorentz algebra. And fancy way, what does that mean? If somebody had to meet this alpha beta, I can immediately write down a representation of a Lorentz group. Right? This I can literally construct that. So good. So now let me package things together in a slightly more compact notation soon. Okay, so let's do it. First of all, I had mi, that was I over 2 that. Right? And then on one side, that. On the other side, you know that that was equal to I0 or 0I. I forget which way, but either way. Good. Right? So you knew that. But then this can be also written as beta square alpha I, because beta square is 1. And then that is same as beta times beta alpha times I. So the reason why I'm packing this way is because later on, pretty soon, I will define beta. I will call a slightly different notation. I call gamma 0. This I will call gamma I. So that looks like I over 2, gamma 0, gamma I. But then what we know is that Lorentz generators are antisymmetric in those indices. Okay? Because if you recall, the way Lorentz indices appear is there was this antisymmetric parameter attracted to the generator. Those are all antisymmetric. So what that means is that I'm going to read off a, so I can decompose this into 2, right? Half symmetrized, half antisymmetrized. So I know that because of that property, this won't contribute. Therefore, for instance, boost generator can be written as like so. Okay, so I'm just rewriting things, but soon I will more, properly introduce all these notations. But I'm anticipating that's coming. Let's do the same thing for this. So what was Lorentz generator? Lorentz generator can be written as, are we having trouble? We have fire? I mean, this is not a blasting sound. It's not happy birthday sound. Isn't it? Okay, let's continue. So I'm going to rewrite the Lorentz generator also. So let's just recall how that looked like. F of epsilon ijk j of jk. So this was the Lorentz generator. And this was L of I. Okay, so that was originally defined. And half, once again, because there's antisymmetry here, antisymmetry there, so just avoid a double counting. Okay, that was one sort of expression. In terms of this, we got that. Okay, assuming I did everything right. No, already find that typo. I. Right? Good. So what do I have? I have minus I over 8 epsilon ij Well, this is what's for the K, so I'm just going to write for the I. Okay, so I of K, I'm sorry, K. Sorry, but you know what I meant. Yes? K. Okay? So, makes sense, right? If I set this to be I, cyclicity, that's the right answer. Okay? Almost there. So I'm going to write this in terms of either gamma 0 or gamma I, which up to beta, I have to do it. So this is equal to I over 8, epsilon ijk, beta squared. Okay, so I just put in 1 there. Then, okay, so J of I0 was that. So here, I want to half, so let me pull out half epsilon ijk, okay, minus I over 4. And then you can put it in. Let me first write, and then let me state the answer. I mean, now, basically, I have finished it. So you should convince yourself that that expression is exactly the same as I over 4 gamma j. Okay, it's a matter of writing equivalents, if you like. Okay? Expand, and the past data. That's all you need to do. So what have I discovered? Well, turns out that starting from this alpha beta matrices, I can construct Lorentz generator J of mu nu for spinor representation, which I will also show immediately, and also be written as gamma mu nu, where I combine gamma 0, gamma I together to call it a 4-vector gamma mu. Okay, so where gamma mu was beta vector. So that was a gamma I, that was gamma vector. Okay, so this is almost good first step to show that that data of alpha beta that fulfills Dirac algebra is sufficient to almost immediately write down a representation of Lorentz group. Here's the answer. Okay, now what I need to show is that this is actually for Dirac spinor. Okay, that I need to finish. Other than that, pretty good. So I found some representation. The question is, what representation have I found? So that's the question. So what representation? Well, let's do step by step. First of all, we talked about 4x4 matrices, alpha beta. That means that these are 4-dimensional representation, which means that whatever that is, if I get a spin J representation, it should be that. Right? So what are the options? So here are the possibilities. For instance, I can have, I don't know, 3 have 0, or 0, 3 half, or half. Remember, these two words basically commute, so I just need the product of the 2 dimensions. Or, I'm going to do this in the second line. Half 0 times half 0, or 0 half times 0 half, or that. I think I probably exhausted. Those are possible candidates, just based on the dimensionality of the representation. Next. So the difference between the top line versus the second line, right? These versus that is the spin of the representation, right? So far I just looked at the dimension of the representation. So let's check the spin. So in order to do that, let's just look at LZ squared. Because we know that representation under the rotation can be traced up and down through this LZ value. So what is LZ squared? Well, I knew how LZ is written. For instance, here, basically same expression. with the permutation of the stuff. But again, G X Y. Okay, one both right? No, did I make a mistake? It should be 2 somehow.
It should be not L but N.
Oh, that was like,
In the second line, I epsilon blah blah.
yeah.
I epsilon M not L.
So this is
Second line.
That's
Second.
second line, sure. Well, this is just 3. Oh no, this is M. Thanks.
And minus I.
No, this is plus I, but then the other one is minus. Okay, good. So M is minus L. That is plus. Okay, so it should be half. You can go back and check. Sorry for the typo. Then let's put half here and check. That gives me what? So that part gives me a -4. And then I need to square these guys, these objects. So x, y, x, y. But they anti-commute. It gives me extra minus. After that, alpha x squared is 1, alpha y squared is 1. So that means I get plus 1/4. That means that the possible values of LZ is plus minus half, which means that this representation includes spin plus minus half state. Okay, so that is useful to say these are not the ones. Okay, so one last thing we could do to nail it down in unique representation. I mean, we know the answer, right? But we're just trying to pretend that, wow, we're discovering the answer. We know the answer because we've been talking about this all the time. But we are basically trying to see how that can be derived from this. So third, so we use the dimensionality, we use the spin. Now we're going to use parity to nail it down. Because if you look at now second line, the difference between these three are parity property. Okay? This guy only had a left-handed, this guy only had a right-handed, this one has both left and right. Okay? So parity is the right thing. For that, let's note the following. So if I let M again, it was I over alpha. And then L was like here super schematically alpha squared, right? Because it's L is a commutator of two M's. It's like as if it's square root of alpha. Okay? Why am I mentioning this? So since alpha, beta, anti-commutes, what that means is that M, if I do this, and then they anti-commute, so they comes out with a minus of M. On the other hand, Lorentz rotation, if I do the same thing, beta, L, beta. By the way, beta is the same as beta inverse. If you want to look this as if it is actually similarity transformation. But L is a quadratic in alpha, so when I pass beta all the way, I'm passing this guy twice. Each time I'm picking up the minus sign, but I am doing twice. That comes out to the plus L. Okay? So what have we found? This is exactly the operation. Something that sends a boost to the minus of itself, because boost is shooting something that way, parity flows the direction. Rotation is a product of a R and P, so it's even under the parity. So this is exactly how parity acts on the generators. Yes.
Let me check one thing. I think they should be direct sum.
Oh yeah. In the goodwill-minded guy, this is direct sum. You killed by 45 degrees in your mind. Who see this as product? Not just, yeah, this is everything plus. Sorry, X. This is plus. Clear? Thanks. Good. Yes. It's meant to be plus. Okay, so now I know how parity acts on the generators. Now let's actually figure this out. Now, one important thing is that beta squared is 1. Okay? I mean, you can read this two different ways. Oh, Dirac algebra, this is one of Dirac algebra. Now, after this discussion, now you can also read this as, oh, square of the parity is equal to. Okay, so if you do x twice, you do that. Now, let's assume, consider a representative space. By representation space, I mean just like, in SU2 representation, if you had a spin half representation, you have two vectors up and down, right? If we are talking about spin 1 representation, we have three vectors, right? +1, 0, -1. That's what I'm talking about. Now, then under parity, right? So this will. So let me just define my notation. P times X. But by this I mean this is a parity inversion of one of the states. Okay. Now, because of the Clifford algebra, what we know is the following. So if I look at the beta squared on this representation space, recall this is a 4-dimensional representation, so I will have a 4 of those guys. And this, on one hand, says that because of the Clifford algebra, that should be 1. For suppose let me talk about the normalized space. On the other hand, which is equal to beta exponent. Okay, so on the other hand, this is also read as this inverse beta n. This is actually a square of the px. So let me just say in word. If your representation space does not include parity inversion of something, then such a state doesn't exist. And this is trivial. On the other hand, in order for that representation space is to be consistent with one of the Clifford algebra, you're demanding that that should be equal to 1, right? Which means that such a state must exist. What it means is that your representation space for any state n, there should exist parity inversion state of that thing. Okay, which means that whatever representation I'm generating, starting out with the Clifford algebra, should be parity invariant, and therefore this is going to get. Good. So that's the physics part of the thing that I was saying. So starting out with the Clifford algebra, looks like we are uniquely generating a representation, which is this. By the way, having said that, let me mention one thing. I am talking about the representation, not the theory. Okay? I'm saying this is because you might be confused. If not, that's great. But if you do, I trust it's right there. Let me explain. So why am I mentioning this now? So we talked about just now, starting out this, I generate a representation. On the other hand, I also wrote a theory, which is like a method that looks like that. This. Okay, so that is like writing out the theory. This is like talking about the representation. Okay, representations are building blocks. You can grab them, you can put them together, create a certain theory. Yeah.
I forgot why the beta is related to parity.
Because of this discussion. So starting out with the boost and Lorentz generator, I check how these guys are sandwich, behaving under the sandwich under the beta. And so I found out that the beta indeed performs a parity, action of the parity on the generators. Okay, and then since these guys act as an operator acting on the state, if they are sandwiched by the beta, state will be set, transforming by a left multiplication. Good. So one comment that I'm trying to say here is that I'm not saying that theory, you start out with this input, will always be parity invariant. I'm not saying that. Okay, you can certainly cook up a theory that is maximally parity violating. What I'm saying is that this will hand you a representation, which is one of the building blocks for constructing a theory that on its own will be a parity invariant representation. That's what I'm saying. And then here I just wrote down a minimal theory, which happened to be only made out of that representation and does not include any parity violating local interactions. So this also was a parity invariant theory. Okay, so there's a slight distinction. Good. Any questions so far? Yes.
I think I didn't understand your statement, so please.
Okay, good. So, suppose somebody give me this. Sorry, so this gives me a representation, which means that somebody handed me a Dirac formula, right? Good. Now I can ask myself, okay, can I write down a Lagrangian that may include these terms? These are all parity invariant terms in the Lagrangian. Okay. Then I can ask myself, oh, can I not write down any interaction of that guy with some, either among themselves or with something else that as an interaction term, suppose this guy had a that term, I don't know, let me just write down random stuff. And then suppose you gave me several number of those fields, okay? You gave me, like, for instance, 4 different kind of those fields. Each of them are parity invariant representation. Good. So, but then in addition to that, so suppose I write down this Dirac Lagrange for each of those 4 Dirac fields. What if I write down ij, k, one more, l, and then I'm just gonna have this coefficient. This is one of the possible local interaction I can write down, and then this is Horrendous matrix, okay? And then this can include some complex phase in it. For instance, I have a lot of entries. I can have some complex phase, and then I can cook up a phase in such a way that this as a local interaction is not parity invariant. That's possible. So then I can have a theory which is not parity invariant, but the building blocks are manifestly parity invariant representation. Okay, good. Okay. So to finish up Pauli's theorem, I'm just gonna say it. You can check it. This is just a couple of matrix multiplications. I don't think I need to do that. Remember, what was the mathematical side of the Pauli's theorem? Well, any alpha beta that satisfies the Dirac algebra is equivalent to bio. So that was the statement. Okay, so basically your job is to find, which means that there exists certain invertible matrix in such a way that T, the inverse is alpha W, and then beta inverse is beta W. So one can already show that this is possible to find such thing. I leave you to read part in the Coleman's section of that discussion. I mean, this is, let me just, yeah, you can just read. Or if you want me to say something. It's more, it's a 2 matrix multiplication we have to do. Okay, so this T is a product of, if you like, what time is it? 15. I have a hard cutoff today. So, what? Oh, 15, thanks. Yeah, so Coleman showed that starting out with an arbitrary thing, first suppose that there exists a T such that the first thing is true. Okay? But then that doesn't mean that beta or any arbitrary given this to the satisfied Dirac algebra, this will be already in the form of a beta W. But at the very least, so therefore, that I don't know, you can play the other way around. Suppose it is something that we call beta tilde, which I don't know what it is. However, since even in that picture, they have to fulfill a Dirac algebra. The Dirac algebra is basis independent. By demanding these two, you find that you find that the beta tilde has to satisfy certain structure. So that is, let me break it down. Yes, 0, lambda, lambda inverse 0. Okay, these are the 2 by 2 block vectors. Okay, then you can always find another similarity transformation matrix S that looks like lambda 0, 0, 1. Then you can show that this will bring eventually. First of all, this doesn't want anything on the alpha. You can check by I. And then now this will bring beta tilde, eventually power representation. So you can only find those. Okay, that's what I meant. You can certainly take a look at the book and read it slowly if you want, but whole point is that starting out with any of those alpha beta satisfying theorem algebra, you want to always construct a similar transformation that brings to the power representation. That most basically. But to me, more important lesson you want to keep in mind is this physics stuff. Okay, starting out with that data, you can always construct a unique Perry-invariant spin half representation. That's to me more interesting and important things. Okay. So we're gonna spend from now, I don't know how long, maybe half an hour, a lot with gamma matrices. Some of you may find it fun, some of you might find it boring. Either way, you have to go through it. Okay, so you have to have all these techniques in your hand. Otherwise, your ability to understand concept will be obstructed. It is always true in physics, right? If you are very strong in calculation, you totally master that part, then that part is totally under control. You have much more room to look into the concept and the deeper aspect of it. So it is not, there's no, if you like, detour, okay? It will come back to you 100% sure. So you have to master it. So next thing we want to talk about is gamma matrices. When I took quantum field theory first, I thought that is like half of the quantum field theory. So much about these identities, the trace identities, and compute, loop diagram, a lot of the 8 gamma matrices. You have to collect down to the number and all that. I thought that's the quantum field. Well, obviously not. So this is exactly what I'm saying is that, if you don't master this stuff, then you feel like that is the thing. No, the thing is actually physics, right? You just are blind by those technicalities. So you have to go through that. Okay, so any questions? Good. So remember, our Lagrangian included the following term: m dagger beta. This was one of the terms in the Dirac Lagrangian. Okay. What that means is that it is this combination rather than versus that combination. This is a Lorentz invariant quantity. Right? I mean, our Lagrangian includes only Lorentz invariant quantity. And you also recall that we constructed something, that behaves like a vector, which had dagger, particularly this guy, and then that guy. So now you understand why this is not a Lorentz invariant, because it behaves like one of the zeroth components of the Lorentz format. Okay? So it is that guy which is Lorentz invariant. So it makes sense to define a notation to write this in a more simple way. So we define a Dirac adjoint, not Hermitian adjoint. How do you call this? Hermitian adjoint? No, how do you say this? Dagger? No, that's not what I was asking. You just call adjoint? Conjugate. Conjugate? Or about complex conjugate? No, this is not complex conjugate. Hermitian conjugate. Did I say that at the beginning? What did I say? Hermitian adjoint. Holy shit. Okay, so Hermitian conjugate. Okay, so here I'm defining Dirac adjoint. This is a notation. Okay, this is the bookkeeping notation. So we're going to define psi bar Hermitian conjugate. Yes, not conjugate. It's defined to be Hermitian conjugate times beta. Okay, so I define that. Now let's also define, so this is like column vectors. Let's also define or row vector. Define similar object for a matrix. But in order to do so, let's first recall ourselves how psi transform on the Lorentz transformation. Well, psi of x goes to some representation like so, right? We even know what that representation, which was written somewhere here before. Okay, half 0 plus 0. So we know that. But then in terms of this notation, let's also ask, how is that transforming under that? Well, that will transform like, as if there is a psi dagger transform, which is like g lambda dagger beta. So let's do it. Psi dagger d dagger beta. But I want to rewrite everything in terms of, instead of, now I don't want to keep two different adjoint. That's big headache. So let's write everything in terms of this not the right adjoint. This expression will be written as beta, and then beta, because I started the beta square, that's 1, like so. So then I want to write this, and then I want to now call it a simple notation that this is the right adjoint of the lambda, which means that I'm saying I'm defining a matrix, a direct adjoint of a matrix, which is the same. So let me just write more generally. So if I had matrix A, I'm basically defining a bar, which is beta A dagger beta, like so. Okay, good. So far, just definition. Now let's immediately see. Let's see what this notation teaches us. The properties of this representation matrix in this notation. As we said, this is Lorentz invariant, right? Now this can be written as n times a parameter psi bar psi, and I know that psi bar psi is a Lorentz invariant, even though not the psi dagger psi. So under the Lorentz transformation, psi bar psi goes to psi bar d bar, like so. That's exactly what we worked out. And since this is Lorentz invariant, this should be equal to so, which means that this representation matrix satisfies this nice equation. The problem with having a nice equation is that you don't appreciate the significance of it. Yeah, of course, something dagger, something should be 1. I don't know what, right? It's just 1. Recall that this was not true in general. In particular, even though Lorentz subgroup, rotation subgroup is still realized as a unitary representation, recall boost was not. It's not like e to the I something. Boost was e to the half plus m something, or not m, like a5 something. So they just add up, and then you didn't get the unitary representation. That is still true. Okay, I'm not modifying that. What I'm saying then is that if you invent this notation, it looks like this representation is Dirac unitary. So it's easy to remember. Okay, so now we introduce a notation. Now we're gonna use it and then rewrite a whole bunch of things in this notation. So first, let's start out with this u of mu. U of mu, that and that. But I will immediately insert beta squared, like so. And then I have this alpha, this. And then I'm gonna again insert beta squared. Because then I can rewrite this as, by combining this, dagger beta this, and then this too. So that's nice looking. So it's as if I have some object between psi bar and psi. So if I just rewrite this as there's something between psi bar and psi, which somehow makes this look like Lorentz four vector. Let me just call that to be gamma mu. So you can immediately read off what that means. So gamma mu is beta, beta, alpha. So what that means is this is gamma 0, and this combination is gamma I, which I introduced earlier to rewrite some of the expressions. Okay. Now, it's useful to have explicit expressions. Let me just write out the explicit expression. So in Weyl representation, that we started everything from. So a beta Weyl was 0, 1, 1, 0. And then alpha Weyl was minus sigma, 0, 0, sigma. So from this, you can get the expression for gamma mu, and in Weyl representation, it looks like this. And I defined this object earlier, right? So sigma was 1 sigma, sigma bar was 1 minus 3. Okay? And I wish you to keep in mind that what was useful about being in the Weyl representation. It is good when your physics need to distinguish left-handed versus right-handed helicity state. Okay? Remember, in Weyl representation, this four-component guy was cleanly, nicely divided into left versus right-handed spinors. Okay, in Dirac representation, which is related by the similarity transformation done by this 1 minus 1, then beta Dirac was, see, do I have? Yes, minus 1, and then alpha Dirac was, by the way, there's a whole bunch of minus sign compared to Coleman. So it's your job, make sure who is right. But morally, everybody's right. Because every physics is defined up to minus sign. So we are friendly. So then you can immediately compute a gamma matrix in this basis, and that is given by 1 minus 1 here. Gamma I is given by 0. Example, why am I putting I? Oh wait, that was better located anyway. So I'm just writing down this so that you have a full set of expressions on your hand when you need to compute, when you need to think about physics in different bases. Okay, so let's explore a little bit more about the gamma matrices. Okay, so next thing we can look at is how this gamma matrices, gamma mu, behave under Lorentz transformation. So that we can extract from this behavior. Since I know this guy transforms like a vector, and yet they can be written as this. And I know how these two guys transform under Lorentz transformation. And that will give me how gamma sort of behave under the Lorentz transformation. Okay, so let's do that. So starting out with this, so I'm gonna look at psi bar, gamma psi. So under that guy transformed as P bar. Are you okay if I just write P bar without dropping lambda? Hopefully it's fine. And then this, that. That's one. But on the other hand, I know how this guy transformed because that is a Lorentz vector. That should transform as this. So by matching these two, you learn that as if this guy behaves like this. So this is not quite, like Lorentz transformation, right? Because this is not D dagger D. This is not like adjoint transformation of the four-vector matrices, but nevertheless, you have some nice neat expression. Okay, next. So once you have this, so now basically we are rewriting a whole bunch of things in terms of alpha beta into gamma mu through this math. So then you can check Clifford algebra. Of alpha beta. So alpha I, not gonna write all of that beta square. That is equivalent to saying that now you have a gamma mu, gamma nu, which satisfies 2 times metric, and then 4-dimensional identity matrix. Remember, this is the 4x4 matrices. So right hand side should also be 4x4 matrices. So this is now a formal Clifford algebra. Okay, are we there already? No. Okay, so this may not be fun for you. You know what? This is also not fun for me to teach. Again, this is crucial. And some of the identities we will derive today, I found it to be one of the nicest way to derive. So maybe you want another too. So, meaning Coleman did a great job. So some of the properties of gamma matrices. So in principle, you can type Dirac matrices or gamma matrices on Google, open the wiki page, and then there's a long list, including proof. So I wonder if I give you some of those problems, one that we have how many? 1, 2, 3, 4, 5, 6, 7. Okay. N number of identical solutions, which is not weird, right? Because anyways, it's a mathematics question, so you're gonna go through the same step. But nevertheless, I think it's healthy to do. Once again, whether you give your hand a chance to do it or not is a huge difference. Okay, whether you just saw it versus you did it, it's a totally different question. Anyway, so here is a couple of identities because remember, this was a beta and beta were a Hermitian. So let me remind you, alpha were Hermitian, beta were Hermitian. This is not any physics requirement. This is just chosen to be Hermitian representation of Clifford algebra of alpha betas. So in that scheme, so if I pick that thing, then I'm saying this is true. And once again, in that thing, gamma I, which again is now beta times alpha I, is not Hermitian, but actually is anti-Hermitian. Anti-Hermitian. You can check immediately because if you do the Hermitian conjugate, use the Clifford, you should see this. Okay, so let me not do it. And then another property is therefore gamma mu dagger is up is same as gamma of the down. This is literally combining this expression, rewrite it in a compact 4-vector notation. Finally, this is true regardless. So these first 3 identities rely on the fact that I start out with a Hermitian representation of alpha beta. The last thing is true regardless. You can take 0th component because this is like beta, 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 which is beta. And then beta, alpha I, and you can check. Was that a question or that was like, no? Okay, good. Okay, now in terms of this gamma matrices, now we can rewrite Dirac Lagrangian. So that was, how did that look like? Well, I had a psi dagger, and then I can plot I, alpha, that with this, psi, and then I had M, psi dagger, beta, psi. So that was Dirac Lagrangian. Now, this can be rewritten into gamma matrices. How do I do that? Well, let me insert beta squared here. Okay, that's 1, so I have not modified it. So one of the beta can be combined with that. So that is psi bar. I have beta times this beta alpha started with the Laplacian, and then that immediately psi bar psi. So this is gamma 0, this is gamma I, so that's combined to be gamma mu, L mu, this, so that M. So this is conventional form that you will see everywhere. And we will define another notation, so party of notations. So whenever you see a vector constructed with the gamma matrices, we will call it a slash. If I have a slash, this is O, not A. Okay, that's the notation. And you can check a couple of identities immediately. So this is equal to A squared. For instance, so very quickly see it because I don't want to list entire identity without saying anything about it. So A slash square is A slash A slash. Right? Very good. That was the most non-trivial first step. Okay, everybody's with me. Then you're successful. You're successful theoretical physicist. So now let's rewrite this as A mu, A nu. Oh, what is that? Gamma mu, gamma nu. Now this is a symmetric, right? So I can decompose this guy into symmetric and anti-symmetric combination, but I'm gonna keep only symmetric decomposition. Hooray! So this is now my Clifford algebra, G mu. So half cancels by 2, so that gives me A squared. Good, so things work. Okay. And then there are a couple more identities for slash. I mean, you don't have to memorize anything, because if you know how things work with the gamma matrices, you can just work it out. But sometimes it speeds up the calculation just a little bit. So for instance, now let's check whether you can do this real time. So I'm pulling out A mu, B mu. That gives me anti-commutator of gamma mu. That gives you 2 times metric. So contraction of 2 times metric. That's 2 times A mu B. Done. Okay, so things like that. Okay, so we now arrive at the right Lagrange written in the model form. So that's good. So then, what is the equations of motion immediately in this language? So equations of motion then in the gamma and slash notation. So now you vary with respect to psi bar. Then the equation of motion is immediately I. How do you call this? Partial derivative? Nabla? No. Round? Yes. Good.
Partial round.
Partial is good, round is good. Okay. Good. Now this is your Dirac equation. All right. And then we have done some check that this doesn't look at all like a Klein-Gordon equation, but we nevertheless show it is the case, right? Now here we can do it quickly. So let's multiply this factor on it. But then that times that cancels against that times that, because this is proportional to the identity matrix, it commutes. So that cross term cancels. The only non-trivial thing terms is this squared minus m squared. So I get that squared minus m squared. Acting of psi is 0. But that is minus of slash squared. And we just learned that square of the slash is the same as the square of that thing, which is square. And that is the Klein-Gordon equation. Okay, so things can be now speed up by inventing good notations. Okay, now now a whole bunch of bilinears. Any questions so far? So far, yes.
저 슬래시 정리할 때 저렇게 정리했잖아요.
Yes.
그러면 저 밑에 있는 식 성립을 하려면 A랑 감마가 커넥트해야 된다.
And they do. So this is a chain of number. This is, set of four by four matrices. This is like, A0 times one of the 4 by 4 matrices, A1 times one of the 4 by 4 matrices, and so on. So number commutes with the matrix. Does that make sense to you? So your question was, if I do that, then naively it looks like gamma A, gamma A. How do I pass A out, right? So these are numbers, these are 4 by 4 matrices. Okay, 4 numbers combined into a vector, 4 by 4 matrices combined into, it looks like 4 vector valued 4 by 4 matrices. Right? And number commits with the vector matrices. So I can pass. Yeah. Does that make sense or okay? Good. Any other questions? All right. Good. So spinor bilinears. Oops. And so this is the last. No, this is not the last part of this business. After that, we will have to do. So that means I really have to speed up. Okay. So let's go through that. So let's recall what we have done. So we learned number one, psi bar psi is a Lorentz scalar. Good, that we learned. That's right. That we just talked about. The second, psi bar gamma mu psi, which was a u mu, that's Lorentz vector. That we talked about. But naively, if I have this times that, so this is a 4-component object, right? This is 4-component spinor. This is another 4-component object. So in principle, you expect that there should be 16 components here. Okay, so I'm looking at the spinor bilinear, by which I mean I took the 2 spinors and multiplied somehow, either that way, either that way. Anyway, what I'm saying is that if I look at the spinor bilinears, and depending on what's happening in this X product part, at least I must be able to explain all possible 16 components. Now, this gives me 1, that gives me 4. So that's, I think, less than 16. So for the rest of it, okay, so that's this part. So let's understand that. We can organize this systematically. So this is like psi bar, and then some gamma matrix in the 0th order. And then this one that we just looked at is psi bar, and then gamma matrix is the 1st order, right? Then you see how we should move forward. Okay? What will be the next thing you think I'm going to write down? I heard something. Well, square, right? So after that, I should certainly look at psi bar, and let's look at the square in this notation, by which I mean more precisely, let's look at this. Okay? And then I want to look at the choices of mu and mu, essentially that they're different. Why is that? If they're the same, well, okay, eventually I will show. For now, we can keep it arbitrary mu, but eventually only this will give me something new. Because they're the same, we talked about the fact that Clifford algebra says that this is 1. Okay, and I collapse back to the scalar case. So that's nothing new about it. So to pretend that we are sort of mathematically clean the physicist, next thing we can do is that let's decompose this into 2. So A, I'm going to decompose this into symmetric way. And then B, I'm going to decompose it into anti-symmetric. as you would have expected. Okay, now, for that thing, the first line is just, this is 2 times metric and identity. So that means that this is just metric times that. So entire non-trivial tensorial structure is just the metric times something that we have seen. So this is not a new term, as we expected already. So now let's look at the second term. So here, I mean, I'm going to define, we're defining a lot of stations, but you have to do it. So I'm going to define sigma mu nu as basically that combination, but I'm going to put the I there. A, because everybody defines that way. And B, because with I there, you can check that this satisfies Dirac hermiticity. Okay, otherwise, you'll have more insight. But it's okay. I mean, if you want to stick to the definition without the right, that's totally fine. This is just something. Now, let's ask how this gets transformed. What do you think? What do you think this guy will transform under Lorentz transformation? How? There's only one sensible guess, right? Which is scalar? No.
seconds.
What happened? What? Say it. Tensor. And what kind of tensor? Antisymmetric tensor. Then you can ask, how do I check? That's a great guess. How do you check? Now you're scared. So let's do it. So let's check. So this, let's just check generally like that. And under the Lorentz transformation, you know how to do it. So that guy will go that the bar, I'm going to use this notation, gamma mu d psi, because that's how psi and psi bar transform. And at the same time, the reason why this was nice notation was that Lorentz transformation satisfied Dirac unitarity. We talked about that too, right? And we also talked about the fact that d bar, this. So d bar gamma mu d behaves like Lorentz vector. Again, rotationally, right? So if you combine all of that, you learn that this transforms like gamma mu alpha, sorry, not gamma, lambda mu alpha, lambda nu beta, psi bar, gamma alpha, gamma beta, this. So we learned that even without worrying about the decomposition of this part into a symmetric versus antisymmetric, that as a whole transforms like a Lorentz tensor. So if I'm given a Lorentz tensor, I'm certainly can decompose into symmetric versus antisymmetric. So this one, I know, must transform as a antisymmetric to tensor. Good. So that gives me how many? So I have a 1 here, and I have a 4 here, and then I discover something new, that gives me 6, right? 4 by 4 antisymmetric tensor. Good, so that's 11. I still need to find 5 more. Let's keep going. What will be the next thing I'm gonna write down?
Field function.
What?
Cubic.
Cubic, very good. Let's do it. So mu nu rho. No, that's not rho. Rho. Okay, so that's what I want to look at now. And for the obvious reason, I'm going to look at the case where mu, nu, rho all different. Because any of two are same basically collapses to just a vector, right? That's the rest is two. Rest is one. So I'm just going to look at that. So how am I going to analyze this one? So to this end, let's note the following. So I have chain of 3 gammas, like so. Very good. And this is the same as gamma mu, gamma nu, gammas O rho. Okay. And then sigma square such that sigma is different from either mu, nu, rho. Okay, since I'm living in the 4 dimensions, if I specify 3 different guys, there's always one unique left over. I'm just multiplying data. Okay, good. So therefore, this can be written as somehow gamma mu, gamma nu, gamma rho, gamma sigma, which is a unique product of all different kinds of gammas in the 4 dimensions times gamma sigma, right? Which means that this somehow is, there's a sense that this is equivalent to almost like gamma sigma, where sigma is something which is none of this mu nu rho. Yes? So it looks like there's some sort of a thing, mass between these two. So that motivates me to define one of the object called the gamma phi, because I use 0, 1, 2, 3. You might say, oh, not 4. Okay, this 5 is cool. I'm not going to give you the 0 answer. So let's define gamma 5, because gamma 4 is not good. Because if you go to the Euclidean, it's nonsense to talk about 0. So you have to actually do 1, 2, 3, 4. They actually have to use 5. Okay, so that's the real reason. Anyway, let's define this. So that is, I define as I times convention, gamma 0, 1, 2, 3. Okay, and then we can also show that this is equivalent to 1/4 factorial, and then epsilon mu nu rho sigma, gamma mu, gamma nu, gamma rho sigma. So because you have 4 permutations, right? And then they cancel the 4 factorials. So therefore, with this, what we can say is that if I want to look at the 3 product of 3 gammas, this is equivalent to, which I mean up to psi I and so on, factors of 2 and so on. So first, this is equivalent to looking at gamma mu gamma phi, right? That is so shown here. So far so good. I didn't hear any sound. I don't know what that means. Are you with me? No? Okay. You refused, okay. Oh. Are you with me or no? Okay.
Nearby.
Nearby. Shit. Nearby, okay. How close are you? Okay, so let's look at it. So what is this guy? Up to weirdo, that looks like a second, right? Up to this weird thing that I just introduced randomly, that looks like the second. Now, and then this one only carries a single Lorentz indices. So under the Lorentz transformation, if you work out the same way, which I will also demonstrate, this will be a vector. Now, hopefully you remember that we use the dimensionality representation, we use the Lorentz transformation. And then if we had a more than that stuff, what did we use to distinguish the rest? Dimensionality, Lorentz transformation, parity. Good, we had a beta and the beta squared, that was crucial, right? So looks like so far, this looks like literally vector. Okay, then I have to talk about the parity. Good, let's do it. In this part, let's add a list so that I don't have to rewrite everything later. Sigma mu nu, that guy, that was anti-symmetric two-tensor. That gave us 6. Let's continue. Okay, so let's check the parity. So to do that, let's very quickly check parity of these guys. Okay, and then what we just discovered looks almost like that. So let's just check the parity of that guy. But in order to do so, I need to tell you some of the properties of this gamma phi. So first of all, gamma phi, you can check it because you have an explicit definition. You can check that it squares to 1. And then you can also check that that is permission. Again, you can just check it. And then finally, not finally, there's a whole bunch of other identities with gamma 5, but just for now, finally, it anti-commutes with the original gamma news. Okay? So let's keep that in mind and use that to check the parity property of this guy. So I'm going to do it here. So under the parity, this guy goes to, did I explain to you how psi transform under parity? I did. Basically, I did, because what incorporate the parity? Beta, which was gamma 0, right? That means that psi under the parity, well, by which I mean either x and t, that should go to gamma 0, psi, that's only psi, let me rewrite that again, psi of minus x. Remember, parity maps a field in x and t into a field, linear combination of field in the parity inverted point with some coefficient. Okay, so here the coefficient is the gamma 0. Okay. Very quickly, let's also check how psi bar transform. So psi bar under the parity transform as psi dagger, psi gamma 0 psi dagger, and then bar gamma 0 and x minus x of t, and then that thing is equal to psi dagger gamma 0 minus x of t. That is equal to psi bar gamma 0 minus x of t. Summary: psi under the parity goes to gamma 0 times that thing, but evaluated at the inverted point. Psi bar goes to psi bar times gamma 0. So here, gamma 0 occurs to the left, occurs to the right, but evaluated. Okay, so you can use that. So now, if you look at this, this is quick. So psi bar gamma 0, that was the first point, and gamma 0, psi, again, evaluate the parity inverted point, and gamma squared squared root 1, so this is plus of psi. So what we have learned is that the first object, psi bar psi, A transforms like Lorentz scalar, B under the parity, it picks up the plus sign. So from now on, we're going to call the scalar, whenever we say, means that it transforms like Lorentz scalar, but also it picks up the plus sign under the parity transformation. Okay, so whenever I say parity or scalar, I'm now going to combine these two meanings together. Okay? Good. So then we will see that later that there's some object that picks up the minus sign there. Then later we will say that not scalar but pseudo scalar, just to distinguish that from this guy. Let's quickly check the second guy. We know nothing happened after this, yeah, here. Well, just. Good. So, don't leave. So, whoever has to leave, please go. But who's objecting if I go half an hour, whatever amount I prepared more as a part of the makeup, whatever. In a sense, you have a whole bunch of makeup. Feel free to object. You are a free man, and I'm free. So I'm going to do whatever I want. So, but you can express your opinion.
But you said you had hard cutoff.
That's why I only said half an hour. After that, I will disappear like you'll never be able to grab it. Okay, are we good to go? Because I want to finish all this technicality. And let's talk about quantum field theory next time. How about that? Cool? Cool. That's good. Thanks. Huge. So, going back to the second one, now let's check the parity transformation, okay? So check parity transformation. First of all, let's divide into the 0 component and then ith component there. Good. So then psi bar 0 psi, let's check how that transforms the parity. Then we'll go to psi bar Are you okay if I'm dropping, x of t to the minus of t? That is understood now. Okay, let's do it. Then we go to, that guy go to that way, as we just talked about. And then there's a gamma 0 sitting because of that, and then gamma 0 this. So these two multiply to p1, and then I'm left with one of them. So that goes into plus psi bar gamma 0. What about the gamma I component of the parity? So again, psi bar goes like that, and then I have gamma I, and then gamma 0 psi. But then in order to collapse these two guys, I have to pass. But when I pass, I pick up the minus sign. Right? That's the Clifford algebra. So I get minus psi bar gamma I psi. What that means is that this as a whole Lorentz support vector transforms like temporal component doesn't change, but actual spatial part flips the sign. That's what we would expect for a vector. Right? If you have a vector like x pointing that direction, under the parity it should flip. But time would not flip under the parity. It is a time reversal that flips that direction, right? So this is what we expect for the vector. So from now on, when I say vector, I mean an object transforms like a Lorentz vector under the Lorentz transformation, but under the parity, it does this way. Temporal component doesn't flip, but spatial part flips. Okay? Bless you. So now let's check how this guy transforms. Okay, good. So now let me write psi bar. What do I have? Gamma mu, gamma phi, this. Okay. So first of all, again, this looks like a vector, Lorentz vector, but we're going to check. And then this only has a 4 component because manifestly this has a 4 component. But now let's check the parity. So the only difference between what we have done before already versus now is that, so compared to this, now I'm going to have gamma phi, right? That's the difference. So let's just recycle. So I had a gamma phi, and then I had a gamma phi. Now, in order for that guy to pass on to that, now in addition to, okay, that is already just collapses to 1, right? But then in order to write in the form that was originally arranged into 0 and then phi, I have to now flip these two. That gives me extra minus sign. Are you with me? Are you with me? Okay, so that gives minus sign. Same thing here. So now I have gamma 0, gamma I, gamma phi, gamma 0. So I have to pass twice to pass these two guys and then collapse with this gamma phi. But I have to pass out twice instead of just once. That gives me actually plus sign. Instead of minus sign, there's plus sign here. So we learned that this guy is almost like a vector, but now it transforms oppositely under the parity, right? So we will call that guy to be either axial vector, or sometimes we can also call pseudo vector. Okay, so that is 0, 1, 2, 3 gammas. Now only one left to do. Okay, there's 4 gammas. Let's do it. Oh. Okay. So that definition immediately tells me that looking at the 4 gamma is the same as looking at the gamma phi. Yes? So what that means is that I want to look at the fifth object, which is psi bar, gamma phi psi. I mean, sometimes also put I for some technical reason. But for now, let's just talk about this. So again, this doesn't carry any Lorentz indices, so it looks like scalar. Okay, and then we're going to check under the parity. Again, we're good because where is it? Here. So now I'm going to have a gamma phi here. So now instead of there just a product into plus, I have to pass once gamma phi. But I told you that one of the property of gamma phi is that it anti-commutes with everybody, including gamma 2. What it means is that as I pass this gamma 0 to collapse with this guy, I pick up the minus sign. So I have a scalar but under the parity, pick up the minus sign. So it's almost scalar, not quite. And then we're gonna call that guy to be a pseudo-scalar. And that provides us the last one component. And then you should be convinced yourself that this is total 16 components. So if somebody had you, either through the calculation or whatever, oh, I have some product of, I don't know how that looks like between these two, I'm not specifying this, right? Then this provides a complete basis for that guy. So this should be written as a product of all these 5 objects in principle, right? And then you can fix the coefficient by demanding symmetry, Lorentz contradiction, blah, blah, blah. Okay, so this provides a complete basis for any object that looks like a spinor vibrator. Okay, that's the whole point of this exercise. Question? Yes.
What happened for the cancer on the plate?
Oh, this. You can check too. So we talked about how antisymmetric two tensor behaves under a parity, right? So for that, we introduced a dual tensor in the tensor, and each of them can be parity eigenstate, and then we decompose. Do you remember that discussion? So let me just write down something that possibly can remind you instead of repeating the same exercise. So given antisymmetric two tensor, we can define a dual tensor, which has schematically epsilon mu nu sigma a rho sigma. Okay, and then that discussion came up because we had something like that versus that, as opposed to half and half as a vector representation. Because this one has a dimension 3, this one has a dimension 3. Wait. Yes, right? So then, this is a linear combination of that, that is a linear combination of that. And that is controlled by the parity. So again, you can use that information or that knowledge to check how that guy turns. I'll leave you that. Any other question? Yes.
Now we have 20 independent guys out of the 2 spinor products.
20. Oh,
16.
okay. Yes. Yes.
16. Oh, I know.
Good. Cheers. Good. Okay. So I have one last to talk about. This book we have arranged. So the last thing I want to talk about is I want to. Sometimes it's called the spin sum, but either you can view that as one mysterious identity that somehow you have to remember when you do the computation. But hopefully I will give you a more physical picture them as projection operator. So I will discuss 2 different projection operator. So that just so that you don't lose the way, we introduced 2 different notation or representation for the 4 component spinor. The vial, and then we have this. And with the Dirac, we had up to square root of 2 plus minus, like so. Okay, so we talked about it. Now, this representation is putting everything into the upper 2 component for left-handed vial or helicity state. And then downstairs it is all right-handed helicity. But then this can possibly have both particle and antiparticle. This also can have particle and antiparticle. The right representation is good because now everybody here is a particle, here is antiparticle. But instead, the price you have to pay is that now you have to have both helicity state upper and both helicity state downstairs. Okay? And there's no single representation that you can nicely single out, left-handed particle versus right-handed antiparticle, for instance. Okay? So mixed up. Now, we are going to discuss a spin sum, but more in the language or in the context of projection operator, either projecting out into the particle versus antiparticle. And then I will also introduce another projection that either goes into the left-handed or right-handed, regardless of the representation. Okay, so that's the remaining discussion I want to do. Okay. In other words, what I'm going to say is that I will give you expression of a projection operators that works either of the representation. In other words, if I give you a projection that project onto the particle, you can still use a bar representation. But if you add that guy onto the bar representation, nevertheless, you will single out on the particle component and so on and so forth. Okay, so that's the last thing I want to talk about. But that requires to talk about a spin sum. Question for the plan. Okay, so one thing that we need to quickly talk about is orthogonality. So at the end of the day, I want to quickly show the following. So U vector, remember this is the coefficient of the positive frequency solution, right? That thing satisfies two orthogonality conditions. This and then B for the negative frequency solution also satisfies similar conditions. So let's quickly talk about how to see that, and then finally let me just finish up writing. That also satisfy V bar V equal to 0, V bar U equal to 0. Did I say V? No, this I meant U. And then also, sorry, I'm writing very schematically here, but hopefully you know what I'm trying to write here. So let me first explain the meaning of these equations. So first recall, again, U is for the positive frequency solution, V is negative frequency solution. This is like a particle, this is like antiparticle. U were upward component in the Dirac notation, V were down to component in the Dirac notation. Okay? Now we are checking that because this is two-dimensional space, we can find two bases. And I want to make sure that they are orthogonal, right? But in this Dirac orthogonality sense. Why we cannot talk about the Hermitian conjugate sense? Because that's not even Lorentz invariant. So let's not talk about it. We talk about it, right? So, but if you want to talk about U dagger instead of U bar, then you can talk about this object. And then, zeroth component was exactly U dagger, if you remember that. Anyway, so U's satisfy two, if you like, orthogonality condition. Either you can look at the scalar version of orthogonality. This is like scalar. Or you can look at the vector version of orthogonality. Either works. Since this is Lorentz invariant, you know that something Lorentz invariant must appear, in this case, mass. Since this is Lorentz vector, you know that Lorentz vector should appear, P mu. That's the only candidate we talked about. And B satisfies the same thing. And then crucially, the third property is that U space completely orthogonal to the V space, vice versa, either scalar sense or vector sense. Does that make sense? So basically, there's a world of the U, which is particle. There's a world of the V, there's an antiparticle. There's a nice orthogonality condition, each of them, but these two sets are totally decoupled in this sense. Good? Good. Now, I'm going to quickly demonstrate, these two. Let me leave the rest to you. Yes?
How U bar and V bar are defined?
Good. So since psi bar is psi dagger gamma 0, and psi is U times e to the minus I p dot x. So therefore, using this relation, U bar was literally U dagger gamma 0. Literally the same. Make sense? This is induced expression coming from this effect.
Okay, thank you.
Good. Good. Let's move on. Okay, so now, again, I'm gonna quickly show these two and then leave the rest to you, and then I move on to the discussion of projection operator. Okay, so let's check the first. I think we already have shown the second one actually, right? That's how we actually fix the normalization of that solution. Remember that. So I don't even have to do it. So because of that, let me drop the other indices. This is 2p mu delta. So then if I take this guy, contract with the p mu, that gives me u bar p slash u is equal to 2 m squared delta, right? So that comes from that. So far so good. So I took the second, which again we showed last time, which is given. On the other hand, the equation of motion for u is I slash minus m times p. This gives me the positive frequent solution, gives me p slash minus m u p. Okay? So what that means is that when I see this guy, p slash u, I can replace with m times u. So if I plug back in, again I get u m times u bar, u, but m cancels, that is 2 times delta. That was the scalar version of orthogonality. Good?
M there, to M.
Yes, thank you. Thanks. Good, and then you can do the rest. Good, so let's talk about now spin cell and the projections. But questions, if you have any.
그냥 멍청한 질문일 수도 있는데 저희 감마 뮤 대신 감마 파이도 넣었을 때 특별한 물리량이
So if your question, okay, the question was, instead of gamma mu, we put gamma 5, is there any meaningful like physical quantity we can talk about? The answer is yes. The answer is yes. So let me say in words. I don't know if that's gonna make sense or not. Maybe it does. So in some cases, this sort of expression may capture, some kind of charge. If you have instead gamma 5, it will capture the, some charge of not vector-like charge, but is what's known as axial charge. And for instance, we will talk about it later. Just like this sort of expression is the current for vector-like symmetry, by which I mean the symmetry acts in the same way on both right-handed and left-handed. Instead, if I have gamma mu gamma 5, then I have another sort of current which describes axial sort of symmetry, the symmetry that only acts on either left or right, not both. So yes, eventually we will talk about all those. Okay, so spin cell. Yes, so let me introduce this subject. I have this p mu with some coefficient which I will fix soon. And then I'm going to look at sum over spins. So 1, 2, and u p r u bar p bar. So note that I'm not writing that u bar u. I'm writing u bar. Okay. So if you like. U bar U is like, inner product in the Dirac notation. I'm actually writing down outer product. Okay, so this is sort of a matrix object. Okay, now in order to understand what this matrix really is, we will explore, but also let me write the same version for B. Let me move this. Okay, so in order to understand this, let's take this guy and act on the U, P of S. So because this guy will hit that first, right? And then according to the first orthogonality, that just gives me 2m times delta Rs. since I'm summing over R, I'll just pick up the S. Are you with me? Okay, so therefore this gives me Cu 2m back to UPS. And likewise, if I add this guy on the B, on the other hand, B is inner, because U bar B is 0, they're totally decoupled, this is 0. Okay, good. Now, therefore, I can choose nicely, so this motivates that I can choose Cu to be 1 over 2n, so that now that definition, with that definition, this guy really acts on the U, turning back to the exactly U, and this guy acts on the B space to completely vanish it, right? So that means that PU behaves like a projection operator onto the U space. And you can check exactly the same with the P sub V, because if you take this guy act on the V, once again, from the scalar orthogonality, you back to the V. But if you take this guy act on the U on the other hand, because V bar U is 0, then again, that annihilates it. So that behaves like a projection operators. But let's totally establish that. So in order to do that, let's note the following. So U satisfies the following this equation, and then V satisfies this equation. Okay? So it looks like somehow this annihilates the U, this annihilates V. And I told you that the P sub U annihilates the V. So this tells me that PU seems like proportional to P slash plus M. Okay? And then similarly, P sub V seems like proportional to P slash minus M. Okay, now we just need to fix the normalization. So in order to do that, I just need to work out how this guy acts on the U. So to fix the normalization, let's just work it out. So P slash plus M acting on the U. But then P slash acting on the U, according to the equation of motion, that gives me M times U. Right? So that was exactly equations of motion. Here. So that means I'm getting 2M times U. So just like, if I take this guy acting on the U, I get 2M times that guy. And then that guy give me 2M times that guy. That means that this notation R, U, U bar is actually P slash plus M. Okay? Although this is not normalized projection operator yet, but anyway, this equality is true. And if you like, you can obviously divide it by 2M, divide it by 2M if you want to define a normalized projection operator. Okay? Exactly the same way, you can check immediately that if you have a VB bar, that's P slash minus M. Once again, if you want to have a normalized projection operator, this time you want to divide it by minus 2M. Minus 2M. Let's very quickly check what that's true. So again, let's take this guy act on the V. So P slash V is minus M times V. You get the minus 2M times V. So you just divide it by minus 2M. Okay, good. Okay, 5 minutes. We can do it. Okay, so therefore, instead of rewriting everything at the same time, let me just write, this is my projection operator onto the U space. This is my projection operator onto the V space. Okay, clear? So therefore, you can immediately check that if I take U and then there's an arbitrary linear combination of U's and V's, obviously this goes on to only U, and likewise V the same. For the projection operator, so you can check that. I mean, immediately it's clear. And you can also check that this is equal to what as the projection operator has to satisfy. Clear, because now on this side, you can just add up these two. What do you get? you get minus 2m. You're dividing by minus 2m. So you should check it's just 1. Okay? And finally, you should be able to check that this is either that order, this order is 0. Right? If you take a 2 projection operator on two orthogonal space, obviously it should be 0, which you can check it because that times that is p squared minus m squared, which is 0 if you're on shell. Okay, so these are good projection operators. And projection onto the what? These are already clear, right? So these projection operator project onto U versus V space. And that was in the Dirac picture most clear. The Weil picture, it will mixed up. But nevertheless, it's true. So it doesn't matter whether you use a Dirac spinner, spinner in the Dirac representation or spinner in the Weil representation. So long as you add this guy onto this, the result is that you only pick up the particle component. Okay? And then likewise for the PV. So the last thing I want to talk about is another projection onto the either left or right velocity component or spin component. So the second projection I want to talk about is this operator. So we talked about gamma 5, right? So we already talked about it. So from there, you can now construct another projection operator, which is projection onto the left versus right. And this is defined as 1/2, 1 minus gamma 5. And this is defined as 1/2, 1 plus gamma 5. So this one I actually want to demonstrate you more explicitly. I just need an expression for gamma 5 in Dirac versus Weil representation. So first of all, I mean, this one satisfies all the properties that it has to satisfy for being, projection operators, and then this PL times PR, this is like 1 minus gamma 5 squared, and then I show you that I mentioned that gamma 5 is equal to 1, for instance. So it all satisfies property for being a projection operator. But in order to be totally explicit, let me write this in 2 different representations. I will do the same thing for this. But for now, let's just do this. So in Weil representation, where you can use gamma 5 in Weil representation to see that P sub L is 0, 1, 0, 0, 0. On the other hand, if you use a Dirac representation, we can show that this thing looks like a have. Oh, did I have? Yes. Have 1, 1, 1, 1. Okay, so with this, let's actually demonstrate whether this actually does the job as we wanted to see. Okay, so let's just work it out. Forget this right projection because that's the same thing. So let's check. So let's take in the Weil representation, and then PL times psi Weil, and then PL was a 0, 1, 0, 0, 0, and then for component spinner is only U plus U minus. And obviously this only gives me this. Note that sometimes people write this as a psi over L. Sometimes people also write this as a psi over L, but there's a crucial difference. This is a 2-component Weil spinner. This is a 4-component Dirac spinner. We're only keeping 2 degrees of freedom in it. Is that clear, the difference? This is still 4-component object. We're only keeping the two entries. That is different from saying that, oh, I'm just gonna keep only that guy, but that's an intrinsically 2-component object. Okay, that's a different story. But just to make sure, let's actually do the same thing in the Dirac representation. Then if I do this, what do I have? First of all, I have that, have 1, 1, 1, 1. And then in Dirac, that looks like U plus U minus, U plus minus U minus. So if you do it, square root of one of square roots and half, you see this is like adding these two. So that drops out 2 times U plus half. I have U plus U plus. So as promised, doesn't matter which representation you're using, because I have not specified here representation. This nevertheless projected onto a required homogeneity only. And then the other one, spin sum, that we talked about, only projected onto either particle versus antiparticle. Okay, so that's all for today. Thanks. Young, can you take your Thanks.